documents that NLPQL will run. So typically speaking, once you've stood up a data set, you can use the import mechanism that we have to load data in from different sources, CSVs and databases and such, and you'll have a lot of documents in a Solr repository. We're running Mimic as our sample document repository in this case, but I think there's 2 million some odd documents. We obviously wouldn't want to run those every time, and so we use a limit function. Even when you're doing a query, it can end up being pretty prolonged. So that's why we have that limit before everything. So the first use case that we wanted to describe as an example is one that stems from some of the work we've been doing with FDA relating to finding cardiac overload and just some kind of examples around that. And I'll blow up one more level here. The gist of what we are doing in this first case is we want to find patients who have a low EF or have late-stage congestive heart failure and who are experiencing symptomatic orthopnea. So for those of you who do phenotype stuff with Odyssey, you're probably familiar with the idea of criteria that we might put into a phenotype definition. In future sessions, we'll talk about how you might take an Odyssey structured definition and combine it with a unstructured definition from Clarity and run them together. But for this week, we're just going to focus specifically on Clarity runs. So we're going to start with a really basic example where you can see the code here, ignoring my limit. We've got what might be considered a minimum viable functioning NLPQL. All of these things, by the way, in the documentation, if you go to the introduction and sort of Clarity NLP at a glance, it'll walk you through kind of all the pieces, what is a phenotype name and libraries, and a few other elements that I won't cover in as much detail here, but that's available in the documentation. But the key things to know that are required is that every phenotype, which is essentially the sort of query, needs a name that you provide it. Doesn't need all the other pieces, but it needs a name. And you have to include at least the core library, which is sort of the Clarity core set of libraries to run the algorithms. In our case, we're looking, as the first part of our case, is to find patients with a mention of orthopnea. So in this particular case, we're basically defining out a term set manually. And we're just saying we're looking for the words orthopnea or the British spelling orthopnea. We will show in future examples how you can use term set expanders to use either English synonyms or medical synonyms like QMLS to automatically expand out a term set. In this case, I just manually picked a couple words, orthopnea, and we just basically say we have this has orthopnea. We're going to send a term finder out, which simply looks for terms, and we are going to run that. And so I'm going to run this here. If you were to do this using Postman or something like that, you would just copy this and then, and you would just paste it into the body of a Postman run, and you would just send it, essentially post it to the location
with type text plain.
Mm-hmm. Thank you. And there's an image above of how to do that in Postman. Here we're running it in the actual window just to make life a little bit easier. So I've just submitted a job, and we're going to go over to something called Luigi, which keeps track of our jobs. It may be that this job was, there's one little task pending, and this is a short little task that we built, and so it probably doesn't have too much hard work, but basically it's taking what we've passed in and it's split it into a series of smaller tasks. This is kind of behind the scenes stuff that if you're interested, you can certainly explore, but also is not really necessary to see the output. But basically, when you do submit a job, even a short job like this, it comes back with a lot of different information. The main things that we'll be talking about will be around the results, and we'll show below how to find those results when they come out and how to view them both as CSVs or view them in a results finder. What I went to before was what's called the Luigi status monitor. When you run 100 notes, it doesn't take very long. The status monitor probably is done, at this point. But if you had a big job, it's a good place to keep track of your jobs, and there's ways to kind of look at the breakdown. But essentially, that status monitor is useful when you have a lot of jobs running at one time. So to see the results of our job, there's a couple different things to know. One is that there's two types of results in Clarity. One which we call intermediate results, which is basically anything that's sort of a data extraction process. And then there's final results, which are basically the patients, or in some cases the documents that meet a specific logic, like a cohort criteria. For what we just ran, this very simple NLPQL up here, we didn't define any kind of cohort. We basically just said go and find a term. And so in this case, we have produced only intermediate results. We don't have a final cohort that's been created. And so what we can do here is we can basically look at where the results are, and then we can do one of two things. I can put this in my browser and just click it, and it's just going to download the results to a CSV. If you had submitted this via your API, it would have provided you, again, this intermediate result CSV, and you could just download it here. So that's exactly what I've done. I've just downloaded a set of intermediate results, and I will blow that up here, oops, a little bit less, so that you can see it. But I'll also point out that in this notebook, we are able to just say, can you show me the first few? And it gives an example of the first 5 results. So you can say, did it basically run? And there's a few things to note, even in here. I don't know if it's easier to view here or in Excel. Maybe here's easier. There's a bunch of data coming back. And there's a lot of data that you may not be very interested in, because we just wanted to know, can you find documents that have mentions of certain terms? But it runs some additional things like negation, like the experiencer elements from context. It has the feature name that we gave it, which is has orthopnea, has a report type, has the section that it came from, has the subject or the patient ID, and then it has the sentence that it came from. So if we wanted to dive in and do an analysis and kind of crunch on it a little bit more, you can use whatever your favorite viewer is for CSV. But essentially, all of these basically will be the sentences where we identify that somebody has orthopnea. You will see that there's some cases here that were negated, where the patient, it's either an evaluation for, or there's other information here. And typically, the reason Term Finder may not be something you would use standardly is that it does return negated results or non-patient results and historical results. So one of the convenience functions that, I'm sorry, was there a question? As we go, sorry, certainly interrupt for questions, recognizing that there's a lot of the pieces that may be not totally clear about where that comes from. For example, how negex runs or how context runs. Those things are external libraries that we imported in. But certainly, as we go along, let me know if there's questions. In this case, I'm not 100% happy with the results that I got back. I have some things that are affirmed and some things that are negated, but some of these elements are not necessarily what I was looking for. So I can use something called well, one is I can modify, and I can say I only want affirmed mentions. So I can say for Term Finder, perhaps I only want certain sections, or I only want a certain subject, the patient. I don't want family members, relatives, and so forth. And so that you can put in these kind of modifications and other parameters around Term Finder in order to change it. So in this case, I'm just going to run one that has these additional parameters, and it's going to go through and basically I'll do the same job with some slight tweaks. Now, commonly speaking, people have a very, when you're looking for a term, most of the time you're looking for a positive mention, a non-negative mention, something that's not hypothetical, something where the subject is the actual patient and not the husband or a wife. And in this case, we have a function called provider assertion, which basically wraps all of those together. So if we run a provider assertion, I guess I can just go back up to my results here. So we did one with the term finder, and that now you can see returns only affirmed results because we've said we don't want any non-affirmed results. And if I run the provider assertion version, that will basically do the same thing, except it will also say the subject has to be the patient, and they can't be hypothetical. So I'm going to pause there for a second. We went through a sort of simple example of looking for positive, non-hypothetical mentions of a term, in this case, the term orthopnea, which is a symptom that's commonly found in the clinical note, but often not found in structured data. So it makes for a good example. Any questions on that?
Hi, John, this is Sergio. So I understand that the limit is 100 documents. So from that result said, how do you know how many out of those 100 documents contain the term orthopnea?
Yes, so that's a great question. The way that 100 limit is, and Charity, you can confirm if but is that 100 documents will be what's returned by a core search. So for example, the term set will say go find all the documents containing these terms, but that some of them may not be patient. Will it go up to 100, or in this case?
It goes up to 100 documents. So so what it does is, because you pass in a term set, you're passing in a list of terms for Solr to query. We use Solr as a backend. So what Solr will do, Solr has a TF-IDF weighting on all the documents. So based on that term's TF-IDF score in that document, those 100 documents will return first. So when you do limit by 100, you are kind of like biasing your data set. That's just like a known thing, but we're only doing it for testing, really. But basically, you're just getting back the 100 top documents.
But is it fair to say that while all of them may contain the term orthopnea, that it may be less than 100 if it throws out negated instances?
For provider assertion, it would be. For term finder, it should have, if you do a set on the documents, it should be 100. And then there are things like a lot of times there can be multiple, so there'll be more than 100 most of the time.
So yeah, so that's a good question. Essentially, that filtering down to 100 happens at the level of the document retrieval, which does use the terms. But that next level where it says I'm going to only keep patients that have an affirmed mention or have a patient experience,
the
that
limit
would slice lower.
The limit only applies to the document.
To the original search.
So it doesn't continue to slice.
Exactly. Right.
Okay.
Yeah. Sure.
Hey John, sorry to I have a question.
Yeah.
So if I understand correctly, so you use Solr to retrieve the most relevant top 100 documents, and then ClarityNLP process those top 100 documents. Is that correct?
That's exactly right.
Okay, so now the next question is there a limit on how many documents I can retrieve?
There's not a limit to how many you can retrieve. So if we were to go directly to the Solr instance and run that query manually, if we type orthopnea, I guess, or orthopnea, but just for example, presumably it'll return back. In this case, it's hard to see. Sorry, 12,926 mentions. So yes, there's not a limit to the number. You can erase that limit requirement, and it would go and it would fetch all the documents. And what you would see is that Luigi would take your job and it would split it into many pieces. So I guess if you had 12,000 documents, it might run batches of 25?
So batches of 25 documents.
Yeah.
And then currently our system has 5 workers, but depending on how much capacity your system is, you would have to increase or decrease the number of
so
workers.
So that's the parallel.
Yeah.
Yeah. So
it has 5 parallel workers in our installation.
Okay. Yeah. Our base version, right? So it'd be running 5 at times. If you have 12, I mean, it still runs them pretty quickly.
Yeah, so batches of 25 with 5 workers.
Yeah, I mean, I would say if say you had 10,000, just to make the math easy, and you had, somebody help me, is that 400 batches? 400 batches? That would probably take maybe like 8 minutes or something.
It doesn't take super long. It depends on what you run, the things you run, but
yeah,
it doesn't. Simple stuff usually doesn't take very long, and it just sort of kicks off in the background. But yeah, limit. We also have a feature called debug, which right now doesn't do much besides just creates an implicit limit. If you take those away, it'll run on everything that matches.
And we'll talk more about document sets more extensively in a following session, but we'll touch on it here. And probably the major ways that documents are limited, one is by term set, which is just the terms, of course, to search. But the other ones are document sets, which lets you say, I just want discharge summaries, I just want chest x-rays, and that obviously limits things a lot. And the third is when we talk about using structured cohorts and how you might limit set to only documents from a particular, for example, Odyssey patient cohort, which we'll cover in a future session. So the next piece to our challenge, our case puzzle, is around finding patients with not just a symptom, but with evidence of severe congestive heart failure. So in this case, we're going to want to extract some values from the chart. And the function that we have that's sort of baked in is called value extraction, and it's actually got a pretty extensive amount of documentation, which really takes you through how the algorithm works and what will be returned and the parameters and so forth and different variants. And Richard Boyd is here, really did an amazing job kind of explaining very, very explicitly how you might expect this to behave. I'll show an example here of a very simplistic ejection fraction searcher, noting that there's some really great, more sophisticated methods to find EF, some good papers and so forth on that. But in this particular case, we're going to search for an ejection fraction using this value extraction parameter, and then we're going to apply a logical operation on it. And I'll show you. So this part's just the very same. We give it a name, and we're going to use terms EF, ejection fraction, LVEF. These are basically looking for the kind of terms that would serve as cues that an ejection fraction is going to be discussed. And I'm basically saying to Clarity, in this case, when you find these terms, be on the lookout for things of this value, and I want you to pull all of those back. And once you've got them back, I want to do one other thing here. And in this case, we want to build what we call a final or a kind of definition, a logical definition of a cohort, where we say, in the context of a given patient, we could have limited it by document, but patient's more typical. I want to find individuals who have an ejection fraction value of less than 30. And so this basically is a two-step. One is finding these data extraction, and one is doing the cohort logic. And so we'll run it and then kind of talk a little bit about how that goes. And if you're interested, when this thing is off and cooking, it will start breaking that down into value extractor tasks as opposed to the previous task we did here. But again, most importantly is that we've used this final declaration to describe the patient cohort criteria. And we've also used this context patient, which just means, if you've used CQL before, it just means that I want the patient to be the way that I group things. I don't want to group it on the document level. So this thing's running. Let's see. Okay, looks like it's all done. So I'm now going to do a couple things. First, I guess, actually, I'm going to start by actually taking that intermediate result and just looking at the results from that. And there's a lot of ways I can do that. I can paste in the URL for it. I can use just the same query that we did previously here. And what you can see is that it's basically returning data, but in this case, the data that are coming back are values, and there's the terms that they were found, and you can see the values are all over the place. I'm able to pull out the full sentence, which I think can be helpful. So let me just show you what an example sentence would be, and then we'll talk about how you can do this through the UI a little bit more easily, so you don't have to be clicking all the URLs. But what you can see is that it's basically gone to a lot of different types of documents. It's found mentions of ejection fractions from echoes, from radiology, and when you look at the phrases, you get the kind of stuff that you might expect. Somebody's describing an EF and LVEF. It's finding the various terms, and it's storing the data over to the side, and there's not really hard constraints on the numbers. There are a couple spots where it's picking up additional elements, but basically it's a non-filtered version of these results. If I want to look at the results of the less than 30, there's a couple ways that I can do it. One is I can go to the URL, this main CSV. Two is I can look at what's shown here, and what we should see is that all the values here are 30 or less, because this is the final result set. But really the best way to do it, and the most gratifying
If I want to refresh the page.
And the most gratifying way to do it is through this result viewer, which basically is giving me a list of all the patients who met my criteria, and allows me to go through and look at those patients and look at the text where that information came from. So I'm able to see the original echocardiogram result, where the data came from, and basically be able to validate or refute or comment on the findings there. And so it provides for a quick way to be able to look through and say, okay, yeah, does this look like it's pulling the right information? Am I getting from my NLPQL definition the actual values that I'm looking for? And so we'll talk more about how the interface can be used when you get more complicated types of queries. But the core piece to know is that you can download your results, you can look through the raw results and everything in the UI, as well as download them manually to your CSV on your local machine. And Charity has crafted all of that up, and there's a lot of cool stuff on the framed up for that. But it's really, I think, designed for an end user who's validating data, and may or may not be as useful for someone who wants to get in and mine the results. So something we did there was do a value extraction for quantitative data. In this case, ejection fraction values, and we found ones less than or equal to 30, and everything seemed to work out very nicely. There's also some conditions here, approximately equal, and thanks to Richard, we've got these values with approximations. You can do ranges, you can do min and max, and all of those different elements around your value extraction. But another thing that you guys may be familiar with if you work on sort of the clinical or the data analytics from a data analyst perspective is that sometimes your results are not numeric, but they may be enumerated. Like for a blood culture, you may be looking for something like positive or pos or negative or neg or whatever it may be, and you're not looking for a set of numbers, you're looking for terms. So in this case, in the same spirit of congestive heart failure, we are looking, instead of looking at echo results, or EF and echo results, we just want to look for the NYHA terms, which is the New York Heart Association. We've got a pretty strong contingent from New York up there, so probably pretty familiar. But NYHA is kind of the standard classification for heart failure. And in this case, I want to look for patients that have a grade 3 or 4, and I've used both the Roman numerals and the Arabic numerals to find it. And you may note that I could have done something like get all of them, and then only as my final result set, I just want the ones that meet 3 or 4. I just kind of cut out the middleman and just said, all right, just extract ones that have these values. So I use my enumerated list essentially to constrain, and we could have done the same thing with ejection fraction. We could have just said we only want values between 10 and 30 or 0 and 30. So now we're going to use this key piece here is this enumerated list. Sorry about that. This enumerated list which is going to allow us to run our job looking only for these values 3, 4, 3, or 4. And in this case, I did not define a final cohort. I didn't put any logic in. So once again, it's only going to be a data extraction process. It's going to extract the data, and it should produce intermediate results for me when it's done running. And so it may not be done. So if I hit it, I get an error. I guess it's done. So in this case, what you can see is that it's extracted values 2, 3, 4, etc. from here, but it's probably a little bit easier to view it in something like either the user interface or in your as an Excel document. So I'm going to refresh here, and let's see what my job is. I am. This one's. I'll just do it as a. There we go. So there's the class. So I'm just going to say I just want to look at the features of this, and it's going to give me all the NYJ class results for these individuals. It'll give me the sentences that it came from, so I can see this is the references to the NYJ classes. These are the values and so forth that were found. And so you can go through and you can look at these and identify whether these are appear to be accurate or not. So both of these examples are looking at a similar question, but one we use an enumerated list, and one we use quantitative values. So are there any questions about that part?
Hi, John. This is Karthik. This is great. Question about the term sets. Are you essentially just doing a kind of a free text match, or is there kind of some semantic search done in the middle?
Yeah, that's a great question. So to cover it, the short version is what we did right there was a straight text match. I put in some terms, but we recognize that that's probably more the exception than the rule. And so we've embedded a number of functions into Clarity to be able to take a simple term and extend it. So for example, simple things that are more grammatical, like pluralization or verb inflection, to get the base and automatically extend from that. We've done synonyms that come both from WordNet as well as synonyms that come from Odyssey or UMLS in order to expand terms. And so I think somewhere, Richard, where would I find that NLPQL call to do?
Go to the user
guide.
guide.
There's also example. You can do it in the UI too.
Scroll down the macro.
Oh, term set expansion. Okay. Okay, yeah. So you can make these calls. So if we were to do, you might do something like clarity.lexical variance or plurals, and so you would build a term set from a group. Here's an example. Yeah.
I built it in the UI too, if you want to see it live.
Oh yeah, that's right. Okay, so if we go to
the runner,
runner,
and then click on needs term extension. Yeah, needs term.
Needs term.
It's not a great name.
Okay.
Oh, you didn't show the preview before, but whatever, it's fine.
Oh, you expanded it automatically. I see.
No, I didn't, but it was down. So you can clear it.
Let me clear it. Okay, sorry. To do that again,
you can. I was going to show the macros.
I'm sorry. Basically, what Charity's done is she's used synonyms and verb inflections.
Well, this is an example from Richard. But yeah.
And Richard, in order to show how things get expanded, and so it, and so you can kind of run. And the expansion is a little crazy for this set, but what happens is you can see how it automatically would expand out synonyms and so forth. And so it's always a good idea. We actually have an embedded term set tester in order to be able to see how term sets would work. And in a future version or tutorial, we'll go through really focusing on how you would take term sets to expand out a concept set. here's a nice one with flu, coughing, fever, body aches, and basically how it expands out these.
Okay, perfect. Yeah. So you're using WordNet and Odyssey, and you potentially could expand it to UMLS flexible variants if you wanted to have that later. Okay, cool.
Yeah, we have a namespace sort of notation. So I say clarity.synonyms, it will give you synonyms from WordNet, odyssey.synonyms from Odyssey, and then we could extend that to other sources of data
Yeah.
also.
Gotcha. So your first step is basically doing a free text search, and then the extraction of the NYH class codes and stuff like that. Is that rule based in the sense that you kind of come up with a model saying, okay, you want to extract the class, the New York art class codes because they're generally structured this way, or ES scores are structured this way. I might have missed that earlier.
Yeah, so that's actually a perfect segue. So what we did just now in the value extraction algorithm, the generic value extraction algorithm, was really just make an assumption that we were going to see a certain term followed by data of a certain value nearby that term, which is not a safe assumption to make in all cases or possibly any cases. But the generic value extraction example that we just did didn't rely on any kind of knowledge of EF or class, but instead just said, I'm going to use this general extractor, and I'm going to look at my results and see how we do. But the next example that we're going to right now is exactly to your point. When you have a situation where it's like, no, I've developed kind of an algorithm for finding NYJ, which is a little bit more nuanced than just pull out these values and so forth. How do you integrate that? Maybe if we run through the next example, and then it's not clear, we can come back to it.
Okay, yeah, sorry, I must have missed that earlier. Thanks.
Oh yeah, no, not at all. The short version that we just ran is a very basic find a set of terms and look for values that match within that sentence, and the first value that matches will get pulled. There's some other parameters that you can pick. It's kind of maybe a first round or poor man's extraction for that. But exactly to Karthik's point, and I'll just say the final piece of this was there's no real surprise here, but basically just going to make the point that if you wanted to combine all the things we've done so far and say we've got orthopnea, we've got ejection fraction, we've got NYHA, we've built these parameters, we've built these classes, we've got low EF, severe EF, we've defined severe CHF, and we have people with orthopnea. I basically could take all the pieces that we just created before and say, now I want patients who have severe CHF, meaning class 3 or 4 heart failure, or an ejection fraction under 30, and I also want them to have symptoms of orthopnea, and I can now run that set. And so this particular analysis will run all of those different pieces, and also is a little bit more involved. It has more tasks because it has to be value extraction and provider assertion. So even though it's just 100 documents, it's the same level. It might take, you can see I'm now up at 14 tasks, and if I look at the phenotype that's being run, it's probably spawned all these little guys down here. And so you can kind of imagine that when you've got in this case, a phenotype, which is made up of multiple smaller elements, so low EF, severe CHF, etc., that it needs to kind of conduct these at a this broken down level. So what you're seeing now is it's running through the tasks, and I'm pretty sure that when it gets to the end of it, it's only going to have found one patient from that group because we only looked at 100 documents. If we expand that up to the 500 patients, which 500 documents would take longer to run, but just to show you an example, I did run that earlier here. Let's see, somewhere before I ran all this stuff this morning. My date times with some future things. I think one of these would be it. Yeah, so I ran this earlier, and what you can see is this is a group of patients, 11 patients, when I ran on 500 documents. And in this case, the result viewer does something kind of cool, which is that it groups this in a way that I can review whether my definitions are making sense. So now
You can click on the left now too.
Oh, really? Okay. So I basically, just to go back to it, I said I'm looking for patients who have severe CHF based on these definitions and have orthopnea. And so now it's basically saying, okay, great, we're going to put together these pieces, and we're going to, again, you can look at the notes, you can get a better understanding, but I can look through all the instances of my patients who had both aloia and orthopnea. I didn't put any date constraints, I couldn't put date constraints, and I can use the user interface to quickly see, are these patients, do they match here? And this is a guy you can see, well, this is 3 years apart. It's kind of handy, and the date, sure enough, is 3 years apart. That may not be why you may want to constrain the date and so forth. But the user interface allows you to review that. And then if you click, for example, has orthopnea, it will give us all the instances in which this patient was documented to have orthopnea. So you can kind of drill in along the different components as well. In this case, where this patient was determined to have a low EF. This is an interesting patient in that they had both NYJ class findings as well as EF findings. So I won't overburden that, but that's a combination of all pieces. So the Clarity UI is designed to do that. So we're going to shift gears, and I'm going to shift it over to Richard Boyd to talk about kind of a use case that Karthik brought up, which is like, okay, that's cool. Value extraction seems like it might be handy for like quick and dirty, but most of the time we're like really building algorithms that can do something useful, and we want to be able to utilize these algorithms. So we recognize that ClarityNLP's core algorithms are not going to meet all the needs, and that people need to extend the functionality of what they're doing. So we wanted to do a case where we're trying to capture information on patient race, and needed a custom algorithm to do that. So Richard, I don't know if you want to come over, or you can sit in my spot if you want to.
Doesn't matter.
Just describe.
Yeah, I can describe.
All right. So
So this extension mechanism we have, if you have your own NLP algorithm or machine learning algorithm or whatever, and you'd like to run it in our pipelines on documents, we have an extension mechanism. We call it extensions custom tasks. Okay, a custom task is code that follows a certain template, but you fill in the data processing, unlike the tasks that are provided and built into Clarity Core. So to get a custom task integrated into our pipeline, you need to do two things. First, you need to provide a Python source code file or files with your algorithm in it, and then you need to put it in a place where Clarity Core can find it. And if you look at GitHub in the file tree, we have under the NLP folder a file conveniently called custom tasks. Okay, and when Clarity starts up, it scans the contents of this folder and finds all the tasks in there and does the necessary plumbing to enable you to call these tasks using NLPQL. Okay, so I'd like to work through an example of the race finder task, which is only put together just to illustrate how this would be done. So, John has here in the notebook the core components of the actual code you would need to do this. So, we have a base. What you need to do is define a Python class and give it the name of your task. Here you see the task name parameter. This name is what appears in the NLPQL file. So in this case, I would call clarity.racefinderTask, since that's what I gave assigned to the task name. And then you need to implement a function called runCustomTask, and this is where you hook in your code. So inside of this function, you have access to the actual document text, either as a single string or as a set of sentence strings. Okay, so if your algorithm happens to prefer all the text at once, you can do that, or if you need tokenized sentences, you can use those. So this particular example, I chose to work with the tokenized sentences. And the function call you see self.getDocument sentences, that is the function call you make, and it will return the output of the sentence tokenizer as a list of Python strings. Okay, and that's what's assigned to the sentence list. So the custom code I wrote to find the patient race is called find race. And I call that function and give it the sentence list. And I think it's probably down in the notebook a little way. Maybe scroll down a little bit. Yeah, there you go. Okay, this is the function find race. So it takes as argument the list of sentences, and then the way it works is it steps through each sentence and applies a set of regular expressions to just extract common occurrences of how patient race might be mentioned, such as white female, or African American male, or white 68-year-old, Caucasian, those sorts of constructs. These are all the regexes here. I won't go through all those details, but it looks for common ways of expressing a patient and the race. Okay, and if it finds any matches, if you scroll down a little bit more, if it finds any matches, it will extract. Here, keep going a little more.
Down.
Scroll down. Yeah, just to that fine rate. Yeah. Okay, if it steps through each sentence, it applies these regexes, and if it finds any matches, meaning that it found a mention of a patient race that it recognized, it pulls out the matching text and saves it as match text. It pulls out the character offsets in the sentence in which the match occurred. But to recall from the results viewer, you can highlight the matching text if you know which characters it spans, and that's what start and end are. And then it produces a normalized version of the patient's race. This is where it converts the lowercase and removes any crazy punctuation and just gets a standardized result, such as Caucasian will be returned as white, African American black, etc. This will be useful for something that wants to make use of the patient's race and further processing. Okay, so once it does all this, it then generates what's called a Python name tuple. A Python tuple is just an ordered pair, essentially, a comma-separated list of values enclosed in parentheses. A name tuple lets you assign a name to each slot in the tuple. So it builds this race finder result name tuple and puts it in a list. The list will be returned to the caller. Now, for this example here, I just stopped at the first match, since the patient's race isn't going to change throughout the note, and once you find one mention, that's probably all you need. Okay, so the result list that you see here will always have just one entry, if it happens to find a match. So then it checks the result list. If it did find a match, it then writes some output. And this is a very flexible thing here that Charity's built in. You can essentially create a key value store, and the keys will show up in Mongo essentially as column headers, and the values will be what's appropriate for that particular sentence that match. So this example you see here, I'm writing out 5 things. The sentence, which is the matching sentence, the start and end character offsets, where the match occurred, the value, which is our default name for the result that's being returned, and then the normalized value, which is the normalized race that we saw above. So I create a Python dictionary, which is this object here, assign the keys and values, and then just write it out. Now, there are other things that go into the Mongo output, but from the point of view of your custom task, that's all the output that you need to generate. Okay?
And most of this is really just copy paste from the documentation, some of these things.
Right, so what John is showing now, where it starts limit 100, this is the actual NLPQL file that you can use to run this race finder task on a set of documents. So in this example, it's running only on discharge summaries, since those tend to mention the patient's race a lot. And then you see the race finder function, clarity.racefinderTask, that's where you actually call this custom task we just described, okay? And since we didn't use a file construct, as John mentioned earlier, the results we get will appear in the intermediate output, intermediate results, CSV.
And so I just ran the NLPQL that Richard described, and it's probably going to cook for a second until it's done. We won't have any results there. But it's going through and it's doing that parsing. While it's doing that, I'll point out that the developer guide has the details about building custom algorithms and example classes and how you can utilize parameters. And I think Richard's example is extremely a good one to follow from. But essentially, what's happening there and how you would incorporate. So this is done. Still, let me just switch over, I think, to one that you shared with me, Richard, that had the results of what you're running. So this would be what the results look like from what Richard did. As he mentioned, the value normalized, the sentences from which it was extracted, and so on and so forth are here, so that you could go through and validate, review, or use them downstream. And I know we're coming up on time, but just make the final point that hopefully is there you go. It's now through here. See it? To make that final point that these can now be all combined. So that we use the custom function to generate rates. We use built-in functions to find things like orthopnea. We use value extraction to find NLPQL terms, and we can wrap all those pieces together, and we can create some type of master organized query that says, "I'd like patients who are Black with severe congestive heart failure, or have a combination of all of those different elements, and put them together." So you'd want to probably have more than 100 documents because it's going to take a little searching to find a patient who meets all those criteria. But we'll leave it at that. So any last questions in these couple minutes?
Hey, John. One other question, just more on the technology point of view, just so I understand. I noticed that I think you're using Solar in the back end. Are you using other infrastructure as well? Because I'm trying to figure out how the Luigi pipeline gets visualized. I would imagine that happens on a cluster or something like that as well.
Yeah, so Luigi has its own mechanism for running, so we just run it as a service that can be deployed, and that's packaged up with our Docker. If you're running it locally, basically you just install it with Python and it runs, but we have it packaged with our Docker, and basically that'll set it up as a service for you.
But broadly, there's about 12 different containers running, including
there's a lot going on.
Including Mongo,
we have
DB,
so
Solar,
results are stored in
Postgres,
Mongo. Yeah, there's a lot going on.
So yeah, there's 10, 12 different containers going on. Yeah.
And the container that's kind of doing the processing, like the nega, like the kind of the custom extraction of terms, that's a separate container? Because I imagine the first step is you basically pull out the documents that have the NYH class, for example. I'm assuming you're making a Solar request, get those documents, and then you do some extra kind of extraction from those terms.
Yeah, those do run on separate containers. We don't have them running on separate VMs, but you could do that. But yeah.
But right, the first phase is that Solar.
Right.
I'm just trying to understand. You have to highly parallelize the process in the sense of like setting it up on separate machines, or does this all run on kind of one machine, more from an infrastructure point?
With Mimic, we have it running on one machine, but at some point, that's probably not going to be big enough for certain document sets. So eventually, you might have to parallelize it out, either with Solar running on multiple machines, Luigi running on multiple machines, or just the whole infrastructure separated out.
Yeah, I guess the environment, maybe Trey can comment on that, but the environment certainly can be set to point at all different machines for all the different functions, but maybe you have to set up your Docker components a little bit.
Yeah, I mean, depending on how up to speed you are with Docker, and you can spread these containers across different hosts. But there would be, I feel like, some work, I guess, on our end to make Luigi run, spread out some of these jobs. I guess.
Yeah, Luigi can, but I don't think we have it set up by default.
So we can.
Okay, yeah, and I was just kind of curious, because I know you guys also have a Hadoop environment, so I wasn't sure how much that gets incorporated. And I know when we try to do our kind of NLP tasks on a larger data set, we try to do it on that environment just because of scale.
Yeah, so we don't use Hadoop. We haven't for Mimic.
No.
You can run Luigi with Hadoop. I think we would probably have to make some changes on that. But it is technically possible. They just probably have to rework a few things to make that all happy.
Okay, yeah, I mean, we're just kind of brainstorming right now on how to set up our environment and stuff, so, and we already have existing infrastructure, so, all right, yeah, I was just kind of curious. Now, this is really cool, amazing work.
Thanks so much. We really appreciate everybody for dialing in, and we look forward. So feel free to send along any clinical, if you've got kind of an NLP task that you're thinking about or you build algorithms for, we'd love to feature it in one of our upcoming cooking with NLP or cooking sessions. But more to the point, you can contact us offline with questions about any of the other pieces as well. So,
and if you're not on Slack, we can add you to our Slack.
Yeah, we can add you to our Slack channel. Please send us your email. All right. Well, thanks everybody, and have a great rest of your day.
Thank you.